So yeah, welcome back. We just before the coffee break, we finished talking about neutrino masses. I still have some pretty pictures of experiments to show to you, but I think what I'd rather do is I will first do the more theoretical part of the second lecture, and then we show all the pretty pictures from the first and second lecture together. And so in the second lecture, our topic will be neutrino mixing and oscillations, which is of course one of the main ways in which neutrinos are special and one of the main ways in which we observe neutrinos. Let's see, where are we? Okay, so that's part 2, neutrino mixing and oscillations. And so we are starting again by just going a little deeper into the 3 flavor structure of the neutrino sector. So 3 flavors of neutrinos. 3 flavors of neutrinos. Remember that we had in the beginning of the first lecture, we had looked at the Lagrangian of neutrinos in the standard model, and I will quickly go back to this so I don't have to write it down again. Here, so remember there was this term through which neutrinos coupled to the W, and then towards in the second part of the first lecture, we had introduced the neutrino mass term, which looks like this, for instance. And then we've seen that in order to move to the physical neutrino states, we had to diagonalize this mass matrix. Now, we do this by doing a rotation in flavor space. But of course, that rotation in flavor space will affect the neutrino interaction terms. So when we make the mass term diagonal, then the interaction terms will no longer be diagonal. And that is the crucial part of this second lecture. So we saw that M alpha beta is in general off diagonal. Off diagonal. So we had to diagonalize it. And doing so meant a rotation of the form nu alpha L equals u alpha j times nu j L. So here, what I call nu alpha L are the neutrino flavor eigenstates as before. So these are the flavor eigenstates. These were the fields that we've had in the Lagrangian in the first lecture. And these fields now, these are the ones of definitive mass. So this is now the basis in which the mass matrix is diagonal. So we call them mass eigenstates. And finally, this matrix that does the transformation, that's the unitary mixing matrix. So the way this mixing matrix is defined, well, by the requirement that the mass matrix has to be diagonal. So for the case of a Majorana mass term, this means that U transpose times M times U is supposed to be a diagonal matrix with the 3 mass eigenstates M1, M2, M3. And this only works because we had the requirement that M alpha beta had to be symmetric. This only works because M alpha beta was symmetric. You can, of course, still diagonalize a mass matrix also for Dirac neutrinos, but then you have to apply two different unitary rotations to the left-handed fields and to the right-handed fields. And only the rotation of the left-handed fields is then the one that is really the physical mixing matrix. So let me also mention this here. Note for Dirac neutrinos. The mass term was sum over alpha beta m alpha beta nu alpha left bar nu beta right. And then the transformation to get this diagonal was nu alpha left is defined as u alpha j times nu j left. And then we need to do a separate rotation for the right-handed fields. Let's call that matrix V beta j, for instance, nu j right. So we need to do two unitary transformations, which are then defined via u dagger times m times v is a diagonal matrix. So as physicists, we call this a diagonalization. As mathematicians, we would call that a singular value decomposition. And that works for really for general complex 3x3 matrices. Remember, the mass matrix for Dirac neutrinos could have been a completely general 3x3 complex matrix. So this works for general complex m alpha beta. Now, once we've done this, I already mentioned that this, of course, has an impact on the neutrino interaction term. So in the mass basis, the Lagrangian, let me see, should I write down? Yeah, let me write down all the terms again, just to make it clear which ones change and which ones don't change. So the kinetic term has exactly the same form in the mass basis as in the flavor basis. Just I'm now summing over masses rather than over mass eigenstates rather than flavor eigenstates. But because there's two neutrino fields and I rotate both of them, the mixing matrix cancels out. Then the charge current interaction, that's the one where the most important change happens, because that one now receives an insertion of the mixing matrix. So this now reads W mu nu j L bar times u alpha j star times gamma mu times E alpha L plus the Hermitian conjugate. Then the neutral current interaction term again remains unchanged because the mixing matrix cancels out. So that's a sum over J Z mu nu J L bar gamma mu nu J L. And finally, the mass term, well, by definition, the mass term is now diagonal. So for Majorana mass term, this is now just a sum over the mass eigenstates, 1/2 times the corresponding mass eigenvalue, nu J left charge conjugate bar times nu J left. And this now means that in the mass basis, a charged current neutrino interaction involves the superposition of all three mass eigenstates. So involves superposition of all three mass eigenstates. So in terms of Feynman diagrams, for instance, the interaction of the W with the electron is now split into three diagrams, for instance, like this, plus the corresponding diagram with a nu 2, plus the corresponding diagram with a nu 3. And the vertex in each of these diagrams contains now a mixing matrix element. So the coupling constant in the first diagram here is g over square root 2 times ue1 star. In the second diagram, it's g over square root 2 times ue2 star. And in the third diagram, it's g over square root 2 times ue3 star. Okay. Yes.
Why in the interaction term there is only summation over alpha? Don't you have to add also summation over j?
Yeah, of course.
It was a thought.
That's my point. Okay, and now the fact that when a neutrino is produced in a weak interaction, it is a superposition of 3 mass eigenstates. This is what ultimately leads to neutrino oscillations. So how does that happen? So in a CC interaction, we produce we produce a flavor eigenstate because by definition well, we always get this superposition which corresponds to a definite neutrino flavor. And as we've just seen, this is a superposition of mass eigenstates u alpha j star times nu j. Similarly, when we detect a neutrino, that typically happens through a charged current interaction again. So in a sense, that is again a measurement of the neutrino flavor. So the CC detection process maps the neutrino again onto a flavor eigenstate. And we call that state nu beta, and we're writing it as a bra vector here for later convenience. So that state is now u beta k nu k, and the summation over j and k is now implicit because I don't want to write so many sums. So that means the amplitude for what happens between neutrino production and detection, this amplitude is nu beta times the time evolution of the nu alpha state. So we produce a nu alpha, we time evolve it, and we then map it onto possibly a different flavor eigenstate. So what I mean by time evolution, so remember how time evolution works in quantum mechanics? Well, when you formally solve the Schrödinger equation, what you get is that time evolution is just e to the I times the Hamiltonian. Let me start a little further down. E I times the Hamiltonian times t times nu alpha. Now, the Hamiltonian is a matrix. In this case, it's a matrix in a 3x3 flavor space. So in order to make progress here, well, we need to go to a basis in which that matrix is diagonal, and that is precisely the mass basis. So let's write nu alpha in the mass basis, and let's also write nu beta in the mass basis. So we write nu beta as nu k times u beta k. Then in the mass basis, this is e to the minus I ej times t. And now the original state written in the mass basis is u alpha j times okay, now let me give you not only the time evolution but also the spatial evolution. James L times U alpha J times nu J. So I should probably, so first of all, here I have forgotten a minus sign in the exponent. And let me write this not only as time evolution but also as spatial evolution, because after all, neutrinos oscillate in both space and time. So we write this as evolution in T and L. And then here, that's not just the Hamiltonian, but also plus I times the momentum operator times L times nu alpha. So that's because typically in a typical neutrino oscillation experiment, we measure how far the neutrino has traveled and not how long it has been on its way. Well, the one time we tried, we found superluminal neutrinos. That was a bit embarrassing. So we're not talking about that. So this was now the transition amplitude from a produced nu alpha into a detected nu beta. Of course, amplitudes are not directly measurable. What we measure is probabilities. So the probability for a nu alpha to convert into a nu beta is, well, just the amplitude square. So now in this line up here, remember I have here a nu k bra vector and a nu j ket vector. This, yeah, there is of course a complex conjugate missing somewhere. And in particular, it's missing here. So this product of a bra vector nu k and a ket vector nu j, that is non-zero only when j and k are identical. And because this is an orthonormal basis, when it's not zero, it's one. So when j and k are identical, then this product of vectors here is one. So I can just write this as u beta j times e to the minus I e j t plus I p j l times u alpha j star. And the sum over j is again implied. We now evaluate the square. So what we end up with now there is 4 mixing matrix elements: u alpha j, u beta j, u alpha k, u beta k star. And the complex phase factor now involves differences of energies and momenta. So the energy of the jth mass eigenstate minus the energy of the kth mass eigenstate. And similarly, the momentum of the jth eigenstate minus the momentum of the kth eigenstate times the baseline L. So this is now the term that leads to interference. That's where the oscillations are coming from. That's the interference term. Now you may ask, okay, I'm assuming now here that my mass eigenstate J and my mass eigenstate K have different energies and momenta, and in a sense that's perhaps intuitive because they have different masses, so their kinematics will be different in the production and detection process. However, normally only states with identical energy and momentum can interfere. So what's happening? So what comes to the rescue here is the Heisenberg uncertainty that is intrinsic to any neutrino oscillation experiment, simply because of the fact that when we want neutrinos to oscillate, well, we need to know how far they've been traveling. And that means we need to have a rough idea of where they have been produced and where they have been detected. So they are the uncertainties in their spatial coordinates are not infinite. And this means that their momentum and energy uncertainties are non-zero. And these momentum and energy uncertainties, they are large enough to overcome the small kinematic differences between the different neutrino mass eigenstates, simply because neutrinos are so light. And that's why these states are allowed to interfere, even though they have classically different masses and different momenta. So that's a subtle, but in my opinion, rather important point, and therefore I'm going to write it down. So states with different E and P can interfere only if the E and P uncertainties are larger than EJ minus EK and PJ minus PK. And the only situation in which this is not the case, well, that's an experiment like Katrin, for instance, where you measure the energy and momentum so precisely that you can tell the kinematic difference between different neutrino mass eigenstates. Now, looking at how much of an effort it was to build Katrin, it's clear that in your garden variety neutrino oscillation experiment, you do not have that kind of knowledge. If you do, well, then oscillations will disappear, just in the usual way, like in any interference experiment, right? When you do the double slit experiment and you know through which slit your photons are traveling, then the interference pattern disappears. Similarly, for neutrinos, if you do kinematic measurements that are precise enough to tell you which neutrino mass eigenstate has been propagating, then oscillations would disappear. But that's not the situation that we are normally in. So this is always the case in neutrino oscillation experiments. Now, what is still a bit ugly here is we have still this dependence on time and distance, but typically we don't know t very precisely, just because there is typically a somewhat largish, or at least large enough uncertainty in the exact time at which the neutrino was produced. Think about a typical accelerator neutrino experiment. You can maybe determine the time of neutrino production to the length of the bunch train in your accelerator. And that uncertainty in time is already large enough to justify that I simply integrate over t here from minus infinity to plus infinity. So typically, we do not know t precisely. So the propagation time t precisely. Because the uncertainty in the neutrino production time is much larger than, well, the inverse of EJ minus EK. And even if I had a sufficiently accurate timing system to tell me exactly when my neutrino was produced and also when it was detected, that information is typically discarded when we do a neutrino oscillation analysis. So all of that justifies integrating over this time. So we define a probability P bar 1 nu alpha, 2 nu beta, which is 1 over some normalization constant times integral dt modulus alpha squared. And yeah, this normalization constant, this is chosen in such a way that this is properly normalized as a probability. If I didn't do that, I would get okay, well, let's first do it without the normalization, and then you'll see what happens. So 1 over the normalization constant times sum over j and k. Now my 4 mixing matrix elements, u alpha j star, u beta j, u alpha k, u beta k star. Now from the integral over time appears only in this complex exponential, so that gives me a delta function times 2 pi delta ej minus ek. And the remaining exponential can now be written as a square root e square minus mj square. So now that delta function forces that only states with equal energies but possibly different momenta contribute to the interference term. So I can omit the index on the energy here, minus square root e square minus mk square, and the whole thing multiplied by the baseline. And this exponential can be approximated using the fact that neutrino masses, and in particular neutrino mass differences, are small. So this is approximately equal to exponential minus I times a quantity called delta mjk square, which I'm going to define in a moment, times L divided by 2 times that energy. And this delta m squared, that's just the difference in the squared masses. So delta mjk square is equal to mj square minus mk square. Okay. Now I'm still stuck with this delta function, but what I'm going to do is that delta function is simply going to end up in the normalization factor. So the factor 2 pi times delta is absorbed into the normalization constant. So practically what's happening here is what I've been doing here is I've only considered the transition probability from the produced neutrino state to the detected neutrino state. But of course, the whole process, well, that's a Feynman diagram with external particles and all of that. So the energy conserving delta function that I'm getting here is exactly one of the delta functions that you always get when you evaluate Feynman diagrams in coordinate space. So in principle, that delta function can be removed from this probability describing neutrino propagation and would rather go into the factors that describe the probability of neutrino production and the probability of neutrino detection. So the neutrino production rate and the neutrino detection cross-section. Okay, so that's the generic formula that describes neutrino oscillations in the most general case, arbitrary number of flavors. It's a bit unwieldy because, you know, there's these two sums, there is 4 different mixing matrix elements, then there is this exponential, which still depends on 2 different indices. So it's often convenient for illustrative purposes to look at the 2 flavor limit. So if we consider only 2 neutrino flavors, then the simplification that happens is that the mixing matrix is now just a 2 by 2 matrix, and a 2 by 2 unitary matrix is just a rotation matrix. It's parameterized by a single parameter, a mixing angle, which we call theta. And it has this form cos theta sine theta minus sine theta cos theta. And then the oscillation probability greatly simplifies. So from one neutrino flavor into the other, this is then approximately equal to sine square 2 theta times sine square delta m square. So now there's only 2 mass eigenstates, so I don't need to put indices on the delta m square times L divided by 4e. And here, so this is in the 2 flavor approximation. So now that's a much more accessible formula. There is one term here, sine square 2 theta, that determines the oscillation amplitude. So it depends only on theta, so only on like a fundamental parameter of nature. So that's nothing that that depends on the exact experimental setup. Whereas the second term, this one here, this is the actual oscillation term, so the one that changes with baseline. So this is the one that I have some control over experimentally, because I have the freedom to determine the baseline and I have the freedom to determine the energy. And this term also tells me the distance over which neutrinos oscillate, namely so what we call the oscillation length. This is the distance over which this goes through one full oscillation, so from flavor alpha to flavor beta and back again. So that corresponds to the condition that delta m squared times L osts divided by 4e, ugly 4, should be equal to pi, which is equivalent to saying that the oscillation length is 4 pi times e divided by delta m squared. So in other words, higher energy neutrinos have longer oscillation length. And also neutrinos with larger mass differences have smaller oscillation length. So in the standard model, we know what the oscillation lengths are. So, or let's not say the standard model, because we can argue on whether neutrino masses are physics beyond the standard model or not, but let's say in nature. So the mass squared differences between the first 2 mass eigenstates is of order 8 times 10 to the minus 5 electron volt square, which leads to an oscillation length of order 60 kilometers at order 1 MeV. And the second mass squared difference, delta M31 square, is of order 2 times 10 to the minus 3 electron volt square, which leads to an oscillation length of order 1 kilometer at energies of order MeV. And then if you have neutrinos of a different energy, of course, it's easy to scale. For instance, when you go to neutrinos of order GeV, then this order 1 kilometer goes to order 1,000 kilometers. And that's, for instance, why an experiment like Dune, which operates at order GeV energies, needs such a huge baseline. So the upshot is the important parameters in neutrino oscillations are the mixing angles, which control the oscillation amplitude, and the mass squared differences, which control the oscillation length. So mixing angle control oscillation amplitudes, and the mass squared differences control oscillation length. Okay. Now there is one. First of all, are there questions up to this point?
So we have used quantum mechanics to calculate the probability of the oscillation, but since neutrinos travels close to the speed of light, shouldn't we use quantum field theory for this calculation?
We've used relativistic quantum mechanics.
Yeah, or that one.
Yeah, so that's fine. Quantum mechanics. So just the fact that the process is relativistic does not yet necessitate quantum field theory. The point where you need quantum field theory is when particle creation and annihilation play a role, when you have particle production and destruction processes. And yes, you can do the same in quantum field theory, and that's actually the comment I wanted to make next, because it's a topic I really like. So the way you do this in quantum field theory, well, there's different ways, but one way that I find particularly elegant is, well, you write the whole, you describe your whole neutrino oscillation experiment as a large macroscopic Feynman diagram. So in QFT, neutrino oscillations can be described as a Feynman diagram. Can be described as a Feynman diagram. So, and the way this diagram looks is, for instance, you start with a neutrino production process that involves a W boson. So let's, for instance, assume there's a process that converts an up quark into a down quark, and there is an intermediate W, which makes a positron and a neutrino. Now the neutrino travels over a long distance. So here's the neutrino. And then on the detection side, let's say that neutrino makes an electron or a muon by again converting this time a down quark to an up quark. So the left-hand part of this diagram here, that's neutrino production. Then here on the right, that's neutrino detection. And here in the middle, this is now, it's still a Feynman propagator, but it is a propagator that describes propagation over a macroscopic distance. So in order to compute oscillations that way, you need to somehow account for the fact that well, neutrinos are produced in one region of space and detected in another region of space. So the typical way in which we evaluate Feynman diagrams doesn't work here, because when we typically think about Feynman diagrams, we treat all particles as momentum eigenstates. Now, a momentum eigenstate is a plane wave, so it is infinitely delocalized in space. So that doesn't work here. So what we need to do instead is we need to treat the external particles as wave packets. And that accounts for the fact that they are localized to a certain extent in space, but also to a certain extent in momentum. So effectively, you write down your Feynman amplitude, and then you integrate over the momenta of all your external particles multiplied with the appropriate wave packet weight factor. So you have an integral that then involves, for instance, a lot of Gaussian integrals, but Gaussian integrals can be solved. Then the next thing you need to do is this propagator here. Well, of course, you start writing this down just as a Feynman propagator. But then in order to get something useful out, you need to make a certain approximation that is originally due to people called Walter Grimus, and the second one was Stockinger. I don't remember the first name. They derived a theorem that essentially tells us what a Feynman propagator looks like in the long distance limit. So long distance means very, very close to on shell, because over long distances, off shell effects become less and less and less important. And the upshot is that in this approximation, a Feynman propagator just turns into a complex phase factor, very similar to the one we had introduced when we did this quantum mechanically. Then finally, the last thing we need to take into account is there's 3 neutrino flavors. So there is, or 3 neutrino mass eigenstates. So there is in fact 3 diagrams of this type, one with an intermediate nu1, one with an intermediate nu2, one with an intermediate nu3. And because these 3 diagrams differ only in the intermediate particles, we need to add them up. But the beautiful thing is, by doing that, all the oscillation physics comes out of the formalism completely automatically. We never need to worry about what exactly are the energies and momenta of the different neutrino mass eigenstates. All of that comes out automatically. We just have to worry about the states of our external particles. So I don't have time to actually go through this calculation, but there's a lot of fun things that can be done with neutrino oscillations in quantum field theory. But of course, the outcome is that the resulting formula is exactly the same as in quantum mechanics, up to some correction factors that describe things like decoherence effects, which are typically not observable in experiments. Please.
So while deriving the oscillation probability for the arbitrary flavor eigenstates, you derived also the exponential term where you got the approximation for neutrino masses to be very small.
Yeah.
But like out of curiosity, there are also short baseline experiments and long baseline experiments working on the same concept, but they also have the case of massive neutrino cases. And will that approximation fit into such kind of models or such kind of experiments?
No. So you're absolutely right. So when neutrinos become so massive that let's see, that the mass squared difference, that the masses or the mass squared differences become comparable to the energies, then this approximation breaks down. You can't use it anymore. But in fact, what also happens in this case is that typically the condition for interference breaks down. Remember that interference between the different mass eigenstates was only possible because the Heisenberg uncertainties in the energy and momenta were large enough that I couldn't distinguish different mass eigenstates. Now, when you introduce a fairly massive neutrinos, let's say an MEV heavy neutral lepton or so, then that condition is broken. So then you don't have interference anymore because you're able to kinematically tell apart the light neutrinos from the heavy ones. And so you don't need an oscillation formula anymore because you can't observe oscillations. But there is, in fact, an intermediate regime where you might still be able to observe oscillations, but the formula that is based on the assumption of small neutrino masses breaks down. So what you'd need to do then is, well, you just keep these square roots here. It doesn't look so nice, but you can still, the formalism still goes through.
So is it correct to say that in such case that the neutrino oscillation is only dependent on the L and E?
Let's say the L, the E, and the masses. The masses always play a role because yes, the L and the E that you give the neutrinos, and then how that E is distributed among the different, or no, which energy each individual mass eigenstate has, that is determined by the kinematics of the production and detection process. But it still depends only on L and E, but not just on L over E.
Yeah.
So on L and E separately.
Thank you.
You're welcome. Okay.
Hello, yeah, Professor. May I ask something?
Yeah, there's a question on Zoom, I think.
Can you repeat your question, please?
Can I ask over here? Yeah. So my question is actually when deriving the formula for nu alpha to nu beta oscillation probability. So all these are for left-handed neutrinos or right-handed neutrinos or both?
These are all left-handed neutrinos. So
Okay,
they're
so what if I want to write anti-neutrino probabilities? So that would be for right-handed only neutrinos.
yeah, so for anti-neutrinos, the formalism works in exactly the same way as for neutrinos. But what does not happen is the neutrino oscillations do not convert between left-handed neutrinos and right-handed neutrinos. Well, technically speaking, they can, but the mixing angle for that is tiny, 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 tiny. Remember when we derived the seesaw mechanism, the mixing between the left-handed states and the right-handed states was suppressed by the Dirac mass over the Majorana mass. So this was a suppression by 12 orders of magnitude. Therefore, conversion of left-handed neutrinos and right-handed neutrinos is not of practical relevance typically. So you oscillate either among the left-handed states or among the right-handed states, but not between the two.
So my question is, can you
I think we have a question there in the back, but also one on Zoom. I'm not sure who was first.
I think, Aman, do you have a follow-up question?
Yeah, just a short question. What if there are Majorana neutrinos and they are right-handed neutrinos? So do we affect any probability formula for this? Yes?
So did I understand correctly? The question is, what if there are Majorana neutrinos? And so neutrino oscillations work exactly the same way for Dirac and Majorana neutrinos, because they depend on two things. One thing is the mixing in the neutrino interaction term, and the neutrino interaction term is the same for Majorana and Dirac neutrinos. And they depend on the kinematics of the different mass eigenstates, but kinematics also doesn't care about the Dirac versus Majorana nature.
Yeah, so even if we consider neutrinos as the Majorana neutrinos, then the probability for both neutrinos and anti-neutrinos would be identical.
Not necessarily. So there's one thing that changes between neutrinos and antineutrinos, and that is you take the complex conjugate of the mixing matrix. And if the mixing matrix contains a complex phase, then there will be a difference between neutrinos and antineutrinos. But that is a fact both for Dirac neutrinos and for Majorana neutrinos. So once again, neutrino oscillations are not do not make a distinction here between the Dirac and Majorana case. Yeah.
At what point would decoherence become experimentally relevant?
At what point would decoherence become experimentally relevant? So the problem is, so let me first quickly explain what decoherence means. So I imagine you have a neutrino traveling through space, and that neutrino is described by a wave packet. It is localized to a certain extent, but it's not perfectly localized. And it is a superposition of three mass eigenstates. So we should imagine this as a superposition of three independent wave packets. And because of the different masses, they're propagating at different speeds. And so the faster one will at some point get ahead of the others, so they won't overlap anymore. So they will no longer be able to interfere coherently in an experiment. And the distances over which this is relevant are typically astrophysical. So solar neutrinos are already decoherent, for instance. The problem is that the decoherence length is much, 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 much larger than the oscillation length typically. So what happens is that if your experiment if your detector is so far away from your source that decoherence would be relevant, then the oscillation peaks in your energy spectrum are extremely close together. And your experimental energy resolution is just not sufficient to resolve them anymore. So even though your neutrinos are decoherent, you're not observing oscillations anymore simply because of your limited experimental energy resolution that hits you first. A second problem is, since neutrino oscillations become decoherent only over astrophysical distances, that means we're talking about astrophysical sources. And in astrophysical sources, you cannot very well localize the point where the neutrino is exactly produced. So for instance, in the sun, well, we know this is somewhere within the inner 10% of the solar radius, but 10% of the solar radius is still many, many, many oscillation lengths. So the fact that you have to integrate over this huge volume also kills oscillations or averages oscillations to 1/2 before you start seeing decoherence. So the one situation where I think decoherence could be relevant would be if there was a sterile neutrino, which was much heavier than the active neutrinos, not quite so heavy that we don't see oscillations anymore at all, but just in this intermediate regime that we talked earlier in response to your question. Then I could imagine that in a certain parameter range, you could still see decoherence. So you basically need to come up with a situation where the coherence length is not too dissimilar from the oscillation length. Doesn't happen in the standard model, but I could imagine that for BSM scenarios with sterile neutrinos with the appropriate masses, that could happen.
And what masses would that be?
Good question. It depends a little bit on your neutrino energies. So let me think. The coherence length is given, I don't remember the exact expression for the coherence length. It depends on the size of the wave packets. So yeah, in that sense, it also depends on the experimental setup. So no, I can't give you a number off the top of my head. But if I had to make a guess, it would be somewhere in the KV to MeV range or so for GeV neutrinos, but that's really just a guess. You're welcome. Okay, so these were all really, really excellent questions that gave me a chance to talk about topics that I really like talking about. So thank you for that to all of you. Now, a topic that I also have to talk about, at least briefly, is the fact that there is not 2 neutrino flavors, but 3 in nature. So we've already seen the general oscillation formula that is, of course, still valid in the 3 flavor case. It's just not as accessible. So all I'm going to tell you is what the typical parameterization of the mixing matrix is in the 3 flavor case. And then we are straight away going to move to neutrino oscillations in matter, because I really still want to talk about that, and you'll also need it for the exercises. So 3 flavor oscillations. So the only thing that changes in 3 flavors is, well, we go back to a 3x3 unitary mixing matrix. So and is unitary 3x3. And a general parameterization for such a mixing matrix or let's say that there's of course no unique parameterization, but the one that is adopted in neutrino physics is it's written as a product of 3 2-dimensional rotation matrices, one in the 2-3 sector, and so what I call S23 and C23 here, well, that just means sine of a mixing angle which we call θ23 and cosine of that same mixing angle. Then one rotation in the 1-3 sector, so C13, 0, S13, and the special thing here is that rotation matrix also gets a complex phase. So here minus S13 e to the I delta 0, 0, C13. And finally, a rotation in the 1-2 sector. So all in all, there's 4 parameters, 3 mixing angles, and 1 complex phase. And that complex phase, that's the one that flips sign between neutrino oscillations and anti-neutrino oscillations. So that's the one that leads to CP violation, so a difference in behavior between particles and antiparticles. And what I should say is when I write the mixing matrix in this form, then I have already used all the freedom that I have to absorb phase factors into redefinitions of my fields. So here, phase factors have been absorbed into redefinitions of fields. So if you just from a mathematical point of view you write down a general 3x3 unitary matrix, of course you have more than 4 parameters, but because of physics you can absorb lots of complex phases into redefinitions of your fields, and only one complex phase remains. So I'm not going to say more about this here because I really want to get started with neutrino oscillations in matter, because we'll need that for the exercises. So neutrino oscillations in matter. Okay, so what happens when neutrinos travel through matter? Well, naively, not much happens, because neutrinos interact so weakly that in order to stop them, you'd need a lead shielding that has about the diameter of our galaxy. So at that level, neutrinos do not experience hard scattering when they travel through matter. But there's one process that can be relevant, and this is so-called coherent forward scattering. And coherent forward scattering is a process in which a gauge boson is exchanged, but no momentum is transferred. So imagine you have here, you have the matter that the neutrinos are traveling through. So there's all, let's say, the individual atomic nuclei. Here is the neutrino. And at some point, the neutrino interchanges, let's say, for instance, a Z boson with one of those nuclei. Now, this exchange of a Z boson can happen without the neutrino changing its momentum. So these are here the background nuclei. And because it can happen without the neutrino changing its momentum, I can in principle not tell, first of all, I can't tell whether the process has happened or not. And if it happens, I cannot tell with which nucleus the neutrino has interacted. So I need to coherently sum over all possibilities. So I sum over the interaction here with the third of these nuclei, plus there's a diagram where the Z boson is exchanged with the fourth nucleus, and so on. And because I'm exchanging, because I'm summing coherently over all the nuclei that the neutrino encounters along its way, this can lead to a huge enhancement factor. And therefore, these effects can, in fact, be phenomenologically relevant. So coherent forward scattering is an exchange of a W or Z boson without momentum change. And therefore, all background particles contribute coherently. And so an analogy to this process is, for instance, when a photon is traveling through matter, the photon also interacts with that matter, and we can't tell which atom the photon interacts with. And that's exactly the underlying physics of photon refraction. So that means the squared matrix element for this process is proportional to n squared times GF squared, where n is the number density of the background matter. So number density of background matter. And the fact that the Fermi constant appears is simply because, well, it's still a weak interaction. So it somehow has to know about the weak interaction constant. Now the diagrams I've drawn up here, this is Z exchange, but I wrote here in that sentence that this can also be exchange of a W boson. So how does that work? So the exchange of a W boson can actually only happen between electron neutrinos and electrons. And the process I have in mind here is the following. So you have an incoming electron and you have an incoming electron neutrino. The electron neutrino changes to an electron while the electron changes to an electron neutrino. And all of this proceeds via the emission of a W. And because this is a process in which the initial state contains a neutrino and an electron, and the final state contains a neutrino and an electron, that can still happen without any apparent momentum exchange. So there's, of course, still momentum flowing through this W boson here, but I can be in a situation where the initial electron and the final electron are in exactly the same quantum state, and the initial neutrino and the final neutrino are in exactly the same quantum state. And so this can still be a coherent forward scattering process. But because ordinary matter contains only electrons, this works only for electron neutrinos. If there were muons in ordinary matter, it would also work for muon neutrinos, but there aren't. And that now has to be contrasted with the process I've drawn above, where the neutrino interacts via Z exchange. First of all, Z exchange can happen not only on electrons, but also on protons and neutrons. And it can happen for any neutrino flavor. So for nu E, nu mu, and nu tau. So now I think I would still need order 5 minutes. Is that okay? Or
I mean, if it's better than for the exercises,
I think it is better for the exercises, yes, because there's an exercise on mass exit. So I just give you what you'll need for the exercises, and then we'll wrap this up on Thursday. So let's look at how we describe this interaction theoretically. So there is, of course, a Hamiltonian. Let's call this an effective Hamiltonian because I'm going to integrate out the W boson. So this is then, after integrating out the W boson, the W propagator here is leads to G Fermi. And I'm only going to do this for the first diagram here because the second diagram is going to be the same for all neutrino flavors. So that's not going to be relevant for oscillations because oscillations only know about things that distinguish between neutrino flavors. So the Hamiltonian, yes.
For the diagram with the W boson, there should also be an S channel, correct? In theory?
Yes, there's also an S channel, yes.
Yeah, okay.
Yeah, correct, yeah. So the effective Hamiltonian after integrating out the W reads electron bar, gamma mu 1 minus gamma 5 nu E times nu E bar gamma mu 1 minus gamma 5 E. So the 1 minus gamma 5, these are just the left-handed projection operators because it's a weak interaction after all. And the factors of 1/2 that normally come with the 1 minus gamma 5, they are actually contained in the Fermi constant. Now, what we need to do to make progress here is we apply a Fiat transformation. And the Fiat transformation just tells us that in an operator of this type, I can exchange the second and fourth field. So the above line is identical to the following: GF over square root 2 times E bar gamma mu 1 minus gamma 5 E times nu E bar gamma mu 1 minus gamma 5 nu e. Now, the reason I'm doing this is because I want to separate the electron current from the neutrino current. Because what I'm going to do next is I'm going to treat the electrons not as a quantum field anymore, but just as a classical field. So I'm assuming that these E and E bar are not operators, but I'm replacing those operators by their expectation values. So that's motivated by the fact that my background matter is essentially static. So whatever state that matter is in, I can multiply with that state from the left and from the right, and then just work with the outcome of that, which is just a number rather than an operator. So we treat the electrons as a classical background field. And that means we take their expectation value. And so the way you do this in practice is you write down the state of your background matter, which is essentially a very large number of creation operators applied to the vacuum. You expand your E field, your electron fields in terms of creation and annihilation operators. And then you contract the creation and annihilation operators in those fields with the ones from your background state. And what this gives you is, well, you'll see in a moment what this gives you. So GF over square root 2. So we want to evaluate the expectation value of the electron current here. Whereas the neutrino current remains unchanged. Gamma mu 1 minus gamma 5 nu e. And now it turns out that in ordinary matter, which means matter that is at rest and that is unpolarized, this expectation value should go over everything here. That expectation value is just the electron number density for mu equals 0, and it is 0 for mu equal 1, 2, 3. So in other words, what we have here is square root 2 times G Fermi times NE times nu E bar left gamma 0 nu E left. So I've now written this as a left-handed field. So I've reintroduced this factor of 2 in the projection operator. That's why the 1 over square root 2 turned into a square root 2. So what I have here, what I got out of my electron current is now just a number. That number is what we call VCC, or the charged current Mikheyev-Smirnov-Wolfenstein potential, the CC MSW potential. Now, let me quickly see if I need to go any further for the exercises. Yes, I need to go one step further. So now what does this do? What does this potential do? We now need to go back to the derivation of the oscillation probability. So in the derivation of P nu alpha to nu beta, we had factors of the form. So remember what our complex phase factors looked like. We had these phases which looked like P times L. And now in operator language, that can be written as the Hamiltonian minus the potential squared. So the Hamiltonian minus the potential is just the kinetic energy minus the mass squared. So remember the Hamiltonian is in the two flavor approximation, it's a 2 by 2 matrix. So 2 by 2 matrix in the two flavor approximation. The potential here is also a 2 by 2 matrix. And that's the MSW potential. So remember, we've just derived here this extra contribution to the Hamiltonian, which we have derived. It is a contribution that exists only for electron neutrinos. So only one component of this matrix is non-zero. So that matrix is VCC 0, 0, 0, because this W exchange process exists only for electron neutrinos. And finally, well, here that's the mass matrix. So once again, H minus V, so H is the total energy, but because I want to determine the momentum here, so I need only the kinetic energy. So I take total energy, I subtract the potential energy, that gives me the kinetic energy, and kinetic energy squared minus mass squared is just the momentum. Well, and then there is, of course, the factor of L that just stays. Now we can again use the fact that neutrino masses are small. So I can write this as approximately H minus m square over 2H minus V, using here the smallness of both V and M. So V is still small because it's still a weak interaction. After all, there's still a Fermi constant suppression. Okay, and all I'm going to do now still is I'm going to write this out in 2 by 2 matrix notation, because that's what we need in the exercises. And then in the exercises, we will see how this change in the oscillation phase, how that actually changes the oscillation probability. So in matrix notation, oh, sorry, and here I forgot to multiply by L. So in matrix notation, this matrix H minus m square over 2H minus V. Well, that's the neutrino energy times the unit matrix minus, well, the diagonalized m square over 2H. This is the mixing matrix times m1 square divided by 2E, m2 square divided by 2E times U dagger, and now minus the diagonal matrix describing the MSW potential. Okay, and so what I propose to do is, I mean, I'm of course happy to answer questions now, but maybe at the very beginning of the exercise session, I will give you I will quickly go through this again to remind you and to set you up for the exercises, and only then we do the exercises. Would that work for everyone? So that we break for lunch now.
Okay.
Let's thank you, Joachim.
Yeah, before we break for lunch, just a couple things. Now there are 2 vegan options. So yeah, get them. The other thing is if you haven't signed up for dinner or said yes or no to dinner, please do so. There's a sign-up sheet there. I think most of you have already. Don't forget to put the bottles and the cans in the specific trash bin for that. And the exercises are already on Indico, so you can take a look at it. Okay. And we meet again at
1:30.
let's say 1:30.
Yeah. Okay.
Thank you very much. Thanks a lot. Can I still sign up for the tour tomorrow? I didn't get a chance.
Yes. I'll make the map for you. Yeah.
Ah, amazing.